This review video is going to be review video 22, how to write chemical formulas. So there are a lot of different types of chemical compounds, and the two main types that we're going to worry about in this class are going to be ionic compounds and covalent compounds. So let's just quickly review what the components of an ionic and what the components of a covalent compound even are. In an ionic compound, those are going to be made up of positive and negative ions, or specifically cations, which are positive, and anions, which are negative. Generally speaking, metals are going to make cations. So metals are going to always tend to lose their electrons, which means that they form positive ions, and nonmetals are going to form anions because they tend to gain electrons, giving them a negative charge. So if you're looking at any chemical compound, name, formula, whatever, and you notice that there's a metal in it, that means that you're probably looking at an ionic compound. Obviously, there are going to be exceptions to this rule. There are ionic compounds that do not contain metals, and I'll show you an example of that in a little bit, but most of the time, 99% of the time, if there's a metal in that compound, it's an ionic compound. If you want to make a formula for an ionic compound, the method you're going to use is swap and drop. And swap and drop is just a shortcut that we use as chemists to make neutral formulas for an ionic compound. Because yes, you can logic it out, and I will show you how to do that, but it's just a quick way to deal with it really fast. But to do that successfully, you're going to need information that we're going to write on this periodic table, and you should have on your periodic table, but write it on there if you don't. To do swap and drop successfully, you need the charge of various ions. And on the periodic table, depending on the group that any element resides in, those elements tend to have specific charges. So anything in group 1 is going to tend to have a +1 charge. Anything in group 2 is going to tend to have a +2 charge. Group 3 tends to have, or 13, I should say, tends to have a +3 charge. Group 14 is either a positive or a -4. 15 is going to be a -3 charge. 16 is a -2 charge. 17 is -1. And as we know, group 18 does not tend to ionize at all. So once again, you'll need that information to do swap and drop successfully. Now, in terms of making your formula for your compound, you need to understand two things. One, you need to understand how to do the shortcut, but two, you really need to understand what it means. So let's say that we're trying to bond together magnesium and chlorine. Magnesium is in group 2 up here, and that means that it is going to end up with a +2 charge, as you're seeing down here. The reason it ends up with a +2 charge is because it loses its 2 valence electrons. Chlorine up here is in group 17, so it ends up with a -1 charge, like you're seeing here. The reason it does that is because it gains 1 valence electron in ionic state. And so when these two elements run into each other, magnesium is going to give up its electrons to chlorines. So in the case of this magnesium here, it's giving 1 electron to this chlorine and 1 electron to that chlorine, meaning that to create a neutral compound with magnesium and chlorine, you need 2 chlorines and 1 magnesium to do it. However, you don't want to sit there and draw this out every single time you want to make a compound, so there is a shortcut, and that's swap and drop. To do the shortcut, you just need the chemical symbol and the charge. So we already agreed that magnesium was in group 2 having a +2 charge, chlorine was in group 17 having a -1 charge, and you just take the numbers, switch them, and drop them down as subscripts. So you end up with Mg having a 1 and Cl having a 2. Please note that I did not bring down the positive or negative symbols at all. I just brought down the numbers. And then every time you see a 1, like you're seeing right here, you actually don't need to write the 1. So you can just write that formula as MgCl2. And that is your final formula given the swap and drop method. So again, that was a lot faster than doing this over here. Next example I'm going to give you is copper 2 oxide. So this formula looks a little bit different than the name of the one above it. And that is because of copper. Copper resides in the transition metals, meaning it doesn't have one specific ionic charge. And instead, you need a Roman numeral to tell you what the charge of that transition metal is. And that's why the transition metals will have Roman numerals in their name. But all it means is that that copper has a +2 charge. Oxygen is in group 16, as we're seeing up here. That's oxygen, and so it's going to have a -2 charge. We're going to take those two numbers, switch them and drop them down, and so you're going to end up here. However, what we're aiming for when we make an ionic compound is a neutral formula, and +2 and -2, when you add them together, equals 0. So we actually do not need 2 of each of those atoms to make a neutral compound. So you're actually going to reduce out those 2's just like you would reduce a fraction. And you end up with this written CuO. And again, the reason we can get rid of those 2's is the same reason we can reduce this fraction to 1/1. Because we do not need 2 coppers and 2 oxygens to create a neutral compound. We only need 1 of each. Last example I want to give you involves polyatomic ions. So this is an example of an ionic compound that actually does not contain any metals, but it's still ionic because it still contains a positive ion and a negative ion. Ammonium and sulfate were 2 of the polyatomics that I asked you to memorize at the beginning of the year. Ammonium is NH4 with a +1 charge, and sulfate is SO4 with a -2 charge. Now, when you do swap and drop with a polyatomic, please note that I put parentheses around both polyatomics, and I did that on purpose because anything that's inside of the parentheses, you leave it alone. You do not change the N, the H, or the 4, the S, the O, or the 4 at all. The only thing that is moving are these 2 charges. So that number is going to end up on the outside of the parentheses here. This number is going to end up on the outside of the parentheses there. And so you're going to end up with this formula. Just like that. Again, please note that I did not change the 4's at all. I did not change anything inside the parentheses. All I changed was the charges that were written outside of those parentheses. And your final formula, please recall you do not have to write that one at all, so we can get rid of that one, and we can write this NH4 2SO4. All right? Couple of things. One is every now and again you'll see an odd looking name. So with your transition metals, especially since they can have multiple oxidation states or multiple different charges, typically you'll see a Roman numeral to represent that charge. But every now and again, we don't see that. We actually see a version of their Latin name. So with these two, we have iron 2 fluoride and iron 3 fluoride, right? Iron 2 fluoride is going to be written like this. Iron 3 fluoride is going to be written like this, all right? But sometimes we can use their Latin names instead of words like iron 2 and iron 3. So iron 2 fluoride is also known as ferrous fluoride. Iron 3 fluoride is also known as ferric fluoride. So you're seeing this suffix OUS and this suffix IC to represent the different charges on that iron. Whenever you see an OUS suffix, it means a lower charge. And whenever you see the IC suffix, it means a higher charge. Now, that doesn't necessarily always mean 2 or 3, because certain transition metals can have charges like 1 or 3, or maybe 2 or 4. So all that the OUS suffix means is lower, and all that the IC suffix means is higher. It's not a specific number, it's just lower and higher. So if you see that, you'll know what that suffix means. All right. Next type of compound that I want to talk about is covalent compounds. Whereas ionic compounds were made up specifically of metals and nonmetals 99% of the time, covalent compounds are only going to be made of nonmetals. And as such, they are named differently. They have prefixes in their names that will tell you how many of each element are in the compound. And because of those prefixes, you do not need swap and drop when you make a covalent compound. These are your prefixes. We have mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, and every now and again you'll see dodeca. And they mean 1 through 10, and then dodeca is going to mean 12. So literally, that is the only piece of information that you're going to need to make your successful covalent compounds. Diatomic elements are something that pop up now and again, and they're very important to know about, because when you end up writing chemical reactions, like we're going to do in the next video, you need to remember that they exist, because if you write a chemical reaction incorrectly, you're going to balance that reaction incorrectly and then eventually do math incorrectly. So, the definition of a diatomic element is an element that pairs up and exists as a molecule in a sample of itself rather than just standing alone. And I mean that if we have a sample of hydrogen, those hydrogens are going to pair up together and they're going to exist as an H2 molecule like this, rather than just a single hydrogen atom. So that's what the diatomic means. Di means two, atomic refers to atoms, so literally diatomic elements are elements that exist as two atoms as a pair. The reason that that happens is because these certain elements can fulfill their own octets, meaning that by sharing electrons with another one of themselves, they can have 8 electrons in their outer shell, or in hydrogen's case, 2 electrons in their outer shell. And so the elements that are highlighted in yellow here are the ones that can do it. And this is how I will remember them on the periodic table, because hydrogen is 1, and then the other ones make this little 7 over here on this side. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And again, if you're looking at a sample of just hydrogen or just nitrogen or just oxygen, you're gonna see that subscript of a 2. But that only applies if it's just that element. If that element is part of a larger compound, like say hydrochloric acid or water or nitric acid, then that doesn't apply, because you're seeing that there's only 1 hydrogen in hydrochloric acid. You're seeing that there's only 1 oxygen in water. You're seeing that there is 1 hydrogen and 3 oxygens in nitric acid. So again, this diatomic rule only applies in elemental state, not in a compound. So, knowing those things, let's practice writing some formulas. Carbon dioxide is our first example. So I don't see any prefixes in the word carbon, so we're going to assume that there is 1 carbon. I see the prefix di in oxide, and so that means there's going to be 2 oxygens, and my formula is CO2. For my next one, my first element is nitrogen, and I see the prefix di, so that means there's 2 of them. For my next one, I see sulfide, so that means that my next element is sulfur. I see the prefix mono, which means there's 1 of them, and so I would write this N2S. For my last one, I see no prefixes next to that carbon, so we're going to assume that there's 1 of them. And I see chlorine is my second, and there's the prefix tetra, so we're going to put a 4 next to it, carbon tetrachloride. Now, if you are not directly told ionic or covalent, it is still possible to figure that out and make the formula correctly. You just have to do a little bit of thinking. So in our mixed compounds, my first compound is aluminum bromide. And if you recall, I said that to determine if you're looking at an ionic compound, you need to look for a metal or a positive ion. Aluminum is a metal. Therefore, this is an ionic compound, and I should be doing swap and drop to make the formula. Aluminum is in group 13, and so it's going to have a +3 charge on the periodic table. Bromine is in group 17, therefore it has a -1 charge on the periodic table. And so my final formula is going to be this, because remembering we do not need to write the 1 next to aluminum. We can leave that out. My next compound is nitrogen trichloride. So neither nitrogen and chlorine are a metal, and I'm seeing a prefix. So that tells me I'm looking at a covalent compound, which means I should not be doing swap and drop to make that formula. I don't see a prefix on nitrogen, meaning that there's only one of them. Chlorine is my second element, and I see the prefix tri, which means there are 3 of them. So NCl3 is my formula. Last but not least, I have ammonium phosphate. Now, ammonium is a polyatomic ion. It is not a metal, however, it does have a positive charge, so this is going to be an ionic compound. Phosphate is another polyatomic ion, and that is going to have a -3 charge specifically. Now, if you are confused on whether or not we should be looking at the periodic table or whether we should be looking at the polyatomic ion chart, what I want you to do is I want you to look for suffixes like ate, because if you see an ate or an ite suffix, that means that you need to look at your polyatomic ion chart. But remember, this is an ionic compound, so we are going to use those charges to do swap and drop. NH4 has a +1 charge, and phosphate, PO4, has a -3 charge. So when we swap and drop those, we're going to end up with the formula NH43PO4. If you have issues understanding this, please talk to me in class.